All right. Hello, everyone. My name is Dr. Nicholas Corsipius. I'm your 3A instructor, and this starts our first week of actually learning new content. So we're going to be diving in, starting at just chapter 1 of our textbook, which is an atom-first approach to introducing chemistry. And so that's where we're going to start, is talking about atoms and elements. This is broken up into a series of lectures divided by topics. So this one, we'll actually talk about atoms and the subatomic particles that make up atoms. Just to pick this word apart real quick, subatomic means smaller than atom, right? So by subatomic particles, we're talking about the different particles that are in an atom. There are 3 different types: the proton, the neutron, and the electron. And we'll talk a little bit more about that, but just so you know, that word kind of makes sense to everybody. All right, so, that's just a breakdown here. Let's just start with chemistry and why we have to learn chemistry, why this is like a base science for so many different topics. Chemistry seeks to explain matter and how it changes with respect to energy. Mass is a big part of that because matter occupies space. But yeah, how matter can be changed from one form to another is sort of the basis of what all chemistry is. And the reason why chemistry is in every school in the country and part of our base curriculum is because it has one major success, right? So basically, chemistry as a subject started 1700s, quite a while ago, and the earliest chemists were very successful at explaining how matter worked because they came up with this theory called the atomization of matter. And that is just that everything is made up of atoms. And that might be a fact that you've known for a long time, right? I mean, I think because of where we are in our progress as humanity, that's something that everybody kind of knows from a very young age, this idea that everything around you, whether it be your cell phone or this pencil or even the air that you're breathing, is made up of atoms. But 400 years ago, that was by no means something that was widely accepted, right? And so the early chemists of the world, they pushed that as a theory and they were proven right. And so that's why chemistry remains a base level sort of important science throughout our lives. And what does that really mean? Well, it's this idea that you can take something, anything, again, it could be your cell phone, could be the gas that you're breathing, it could be anything. And if you start trying to divide it up into smaller and smaller parts, eventually you're going to get to one part that you can't divide any smaller. Why they used iPod Nanos in this particular diagram, I have no idea. This was the textbook's diagram, but kind of the same idea, right? You have this basket full of iPods and you start dividing it up, cutting. Eventually you get to one that you can't divide up anymore, right? And that's kind of how matter works as well. You could take this gas that you're breathing and you could start breaking it into two, etc. And eventually you'll get to a part that's no longer divisible. Okay, and that's sort of the atom aspect of it. We'll actually talk about what an element is here a little later. I want to save that for when we introduce the periodic table. But that's the bottom line, is the atom is the smallest building block of matter. All right, so kind of the model of an atom, how people thought about atoms changed quite a bit. The first one to propose this theory of atomization was Dalton, and used it to explain how a lot of the other previous findings that were troubling people, made a lot of sense. A lot of it was based on experiments with gases. We don't really have to talk too much about the theory because it turned out to not be completely correct. I like this picture right here a lot. So this is John Dalton, who gets credit for the first sort of model of an atom in 1803. And this was this idea that everything was built up of atoms, but how he pictured an atom was basically as a solid sphere. So at this point, the early 1800s, the theory is that everything's made up of basically little marbles, right? Super duper teeny tiny solid marble kind of spheres. And that's when an atom was. All right. 100 years later, that got built on because of the discovery of electricity and electrons. And there was this idea that, okay, these aren't just like hard marbles, they're actually composed of even smaller parts that have a charge associated with them. So they were discovered that atoms contained negatively charged electrons. And then that brings us to what model we're going to kind of work with here today, which is Ernest Rutherford's model of an atom, which has a bunch of negatively charged electrons that kind of orbit around a central positively charged nucleus. Okay, he kind of pictured it a lot like how planets orbit the sun. He imagined these electrons were orbiting this center nucleus like this. The positively charged nucleus was in the center, that's the sun, and the electrons are kind of zipping around it like they're the planets. Actually, next chapter we'll kind of graduate to these more complicated models, but this works for us right now. So that's kind of how we want to think about atoms. Atoms have this dense nucleus that contains positively charged protons, and surrounding them are negatively charged electrons. Okay, so this is the Rutherford model. He actually did that using this experiment that we're going to talk about here, where basically he had this very thin sheet of gold foil, and he shot some nanoparticles, or I'm sorry, some alpha particles at it, which you can just think of as being super duper teeny tiny things. With the model that would have been true before, where they didn't know that there was that dense nucleus in the middle, they would have expected every bit of those particles to go straight through. Okay, what Rutherford showed is that actually the middle of the atom has to be this dense nucleus core, because some of those particles came in, but then they got shot back out in the other direction. Okay, so because of that, this is the sort of idea that we have of an atom. Let me actually jump real quick. This is sort of this idea that we have of what an atom looks like. It has a small but very dense nucleus that consists of protons and neutrons. We'll talk a little bit more about those. And then this larger sort of cloud of electrons that are, again, sort of orbiting around that nucleus. So actually most of an atom is made up of empty space where the electrons are kind of traveling through, just like if, again, you think of our solar system, how you have planets orbiting the sun. Most of that is empty space. And then in the very middle, you have this very dense core, which is the nucleus. Okay, so then the idea of having these charged particles is a big part of atomic theory. So we're going to take a step back and talk a little bit about electric charge. Yeah, in chemistry, we have two different types of charged particles. One of them has a positive charge. This is what we call a proton. And one of them has a negative charge, which we call an electron. And when two opposite charges are brought close to one another, they have this effect where opposites attract. Okay, so opposites attract is a key theory of this electrical charge. So a positively charged proton will attract a negatively charged electron. Like charges repel each other. Okay, so opposites attract, like charges repel. So that means if I get two protons close to one another, they'll actually force each other apart. They don't want to be in close contact. Just like same sort of idea, if I get two electrons close to each other, they'll push each other apart. They don't want to interact. Okay, so opposites attract, like charges repel. Not only that, but the intensity with which these like charges will repel each other increases with how much charge they have. So in this example, each one of these particles have a charge of +1, and so they're repelling each other, but kind of weakly. And then over here in this diagram, each of these particles have a charge of +3, and so they very strongly repel each other, right? So depending on the amount of charge you have, it will influence how strongly they repel each other. And likewise, I mean, if this was, instead of being a bunch of negatively charged or positively charged particles, if this was a -3, right? So that was negatively charged, they would very strongly attract one another. All right, so the intensity of the attraction or repulsion is dependent on the magnitude of the charge that you're talking about. Okay, so the intensity of the charge matters, as well as how close together they are. So when these two positively charged particles are farther away, they'll repel each other weakly. If I try to force them together, all of a sudden they'll push each other apart really strongly. So again, the distance between them also sort of influences how strong that repulsion is. And then lastly, opposite charges will cancel one another out, right? So this positively charged particle wants to attract this negatively charged particle. Once they do come together, there's no net charge any longer, right? So it's kind of as simple as a math equation where when you have +1 and you add -1, you get 0. You do the same thing with charges. All right, so then again, this brings us to our model of our atom that we have. Again, the largest portion of our, well, that was terrible. The largest portion of our atom here is this kind of empty space that's occupied by the electrons that are orbiting around that central nucleus. The nucleus and those electrons, again, our electrons are all negatively charged. And they're orbiting this dense nucleus, which consists of these positively charged protons. The other thing that was discovered to be contained within a nucleus was another type of particle called a neutron. Okay, and so we also have in here these red balls here, which are neutrons, and they have no charge. So they don't impact the charge of the atom. They belong to the nucleus. They're kind of stuck in there with the protons all stuck together, just like this picture kind of implies. But they don't have any charge associated with them. So these are our 3 subatomic particles. You absolutely got to know these 3 subatomic particles in this class. They're the basis of like all of chemistry here. Electrons with a negative charge, protons with a positive charge, neutrons which have no charge. All right, so let's go over some terminology here, okay? Some vocabulary. Atoms, which is again what that model that I just showed was, which consists of the protons, the neutrons, and the electrons. When we talk about an atom, they are neutral, which means that they have an equal number of electrons and protons. Remember those, if you have the same number of negative charge as you do positive charge, it cancels each other out, so there's no net charge. When it comes to the number of neutrons, that can actually vary within an atom, within a nucleus, because they don't have any charge associated with them, so it's fine. So atoms are neutral, okay? Same number of electrons and protons. When we talk about ions, those do have a net charge, okay? So those are going to be atoms, but they have more protons than electrons, or more electrons than protons. In that case, we don't call them atoms anymore, we call them ions. And then there's even more sort of fancy terminology. If it has a negative charge, it's called an anion, and that means it has more electrons than protons. Right? So if it's a negative charge, you got more of those negatively charged electrons. Whereas if it has a positive charge, it's called a cation, which means that it has more protons than electrons. Okay. Yeah, one sort of stupid way to remember these terminologies, cation, anion, it's kind of easy to get them mixed up. Cations are positive, right? Cations are positive. It's really dumb, but it definitely helps me to remember. or help me remember when I was in your shoes. So yeah, that's a very easy way to remember which one's which. And so the cations are the ones with positive charges, anions have a negative charge. Okay, so now we're going to talk about how to calculate a net charge within a particle, right? So these are four different, these represent four different atoms or ions here. And given the number of neutrons, protons, and electrons, we want to figure out what the net charge on these atoms or ions are, okay? So that's what we're going to figure out over here in this category, net charge. And remember, what charge does a proton have? So each proton will have a charge of +1. What charge does an electron have? Each electron will have a charge of -1. And then neutrons have a charge of 0. So actually, if all I'm talking about is the net charge, I don't have to pay attention to this category at all. All I'm going to do is compare the number of protons and electrons. Okay, if I have the same number of protons and electrons, right? So 10 protons and 10 electrons, what's my net charge? It's going to be 0, right? They cancel each other out. What if I have more protons than electrons? What would you expect? Would it be a positive charge or a negative charge? Right, since I have more positively charged protons, I know it's going to be positive. And just how much? Well, we can just take the number of protons and subtract the number of electrons, and that will give us our net charge. So in this case, if I take 12 and I subtract 10, I'll get +2, so that's my net charge. Example C is actually the same. I have the same number of protons and electrons, so again, my net charge is 0. And what about with the next example? Again, now I have more electrons than I do protons. So what would we expect the charge to be, positive or negative? In this case, I would expect it to be negative. And if I take the number of protons, which is 17, and subtract the number of electrons, which is 18, I get the charge of -1. Okay, so it's fairly simple to figure out what the net charge on your, in this case, this would be an atom. This would be an ion, this would be an atom, this would be an ion. It's fairly easy to determine, but you want to make sure that that's a skill that you have after this lecture, because that's really important.